In this section, we're going to talk about properties of logarithms. And since logarithms are so closely related to exponential functions, then all those rules that we had for exponential functions are going to have corresponding rules for logarithms. So for example, you might remember the rule that when you have two things multiplied together with the same base, you can combine it by adding their exponents. Well, in logarithms, that corresponds to if you have the logarithm of, let's say, base b, logarithm base b of x times y, that can be written as log base b of x plus log base b of y. Whatever happened to the exponents in the rule for exponential properties happens to the logarithms themselves. Remember, logarithms themselves are exponents. So if in this previous property, when you're multiplying two things together, you add the exponents, then in this multiplication property, you add the logarithms. Now, before I show you the next rule, I want to show you a quick reasoning why. So watch this. Let's talk about log base 2 of 8. Now, if you've been dealing with logarithms, you probably know this is asking what is the exponent we put on a 2 to turn it into an 8. Well, 2 to the 3 power is 8, so this should be an answer 3. But if I use the property above, log base 2 of 8, and I rewrite this as log base 2 of 4 times 2, the property above said that should be equivalent to log base 2 of 4 plus log base 2 of 2. Okay, so, these are two logarithms that we can figure out. What is the exponent that you put on a 2 to turn it into a 4? Well, that exponent is 2. You put 2 on a 2 to make it a 4. And the second one, what's the exponent you put on a 2 to keep it a 2? Well, that exponent is the exponent 1. 2 to the 1 equals 2. And sure enough, 2 plus 1 gives us 3, as we would expect. That doesn't count as a proof of that property of logarithms, but it's a nice justification. Okay, before we do an example, I want to write down the second property of logs that is really closely associated with this first property of logs. So if we call this property 1, property 2 would be log base b of x divided by y is equal to log base b of x. And you might anticipate what's going to happen if when we multiply the two parts of the argument of a log, things inside a log together, that means we add the two logs. Then when we're dividing two parts of a logarithm inside, we're going to subtract these two logs. So log base b of x minus log base b of y. And that would correspond to the rule from exponents. B to the x divided by b of y is b to the x minus y. And the third rule is related to this exponent rule you probably remember. If you have something that's raised to an exponent and you raise it to another exponent, then you multiply that number by the exponent. So b to the x then to the n power is b to the n times x. Well, the corresponding rule in logarithms is this, and this is the last big one that we're going to use. If we have the log base b of x to an exponent n, this is equivalent to n times log base b of x. So remember, whatever was happening to the exponent back in the exponent rules is what's going to happen to the logarithm. So back in this exponent rule, we took the exponent and we multiplied it by n. Here, we're going to take the n and multiply it to the logarithm. Okay, so this one is actually the easiest one for me to show you why, to show you another justification. And I want to show you this. Watch this. Say we had log base b of x cubed. Okay, so we could rewrite that as log base b of x times x times x. And according to our first rule here, if you have the log of a product, you can break that apart into the sum of each logarithm. So log base b of x times y is log base b of x plus log base b of the next thing, of y. So if you have the product of 3x times x times x, that should be broken apart into 3 logarithms, log base b of the first plus log base b of the second x plus log base b of the third x. And these are all like terms, log base b of x, and their coefficients are 1. So 1 log base b of x plus another log base b of x plus a third log base b of x is 3 log base b of x. So instead of doing that every single time, if we had something like, for example, log base 7 of x to the 29th, instead of using this property here and writing out 29 x's, adding all those log base b of x's together and then combining them only to find out we have 29 of them, this rule tells us that we have the shortcut of writing 29 times log base 7 of x. Let's practice some examples that use each one of these rules. So let's put those rules of logarithms up in the corner up here. And the first set of examples, I'd like to work on expanding logarithms as much as possible. Generally, when we expand, we also want to make sure that we leave no exponents in our answer. So let's do our first one. Let's expand log base 8 of 5 times a divided by b. Okay, first thing I'd like to point out is that the 5 and the a up in the numerator are being multiplied. So I can actually use rule 1 with the 5 for x and the a as y. The b is being divided, so I can use rule 2 and make sure that whatever's being divided goes into the logarithm that's negative. So if I expand as much as possible, that'll look like this. Log base 8 of 5 plus log base 8 of a minus log base 8 of b. Done. Let's do another example. Let's say we're going to expand ln of the quantity x cubed y squared over z to the 3.7. Okay, so for starters, again, want to point out that in the numerator, I have multiplication. And in both the numerator and denominator, we have a lot of exponents. I can't yet use rule number 3 because each one of these exponents only applies to part of the logarithm, part of the inside of the logarithm rather, not to the whole thing. So I'm not ready to use rule 3. But we can use rules 1 and 2. So we can write this as ln of x cubed plus ln of y squared, and the denominator minus ln of z to the 3.7. And then finally, if we're not supposed to have exponents, we need to get rid of the 3 and the 2 and the 3.7, but now because this is just ln of x cubed, and the cubed is applying entirely to the x inside the log, now I can use rule 3. So this will become 3 ln of x plus 2 ln of y minus 3.7 ln of z. Okay, let's do one more expanding. Let's do log base 2 of the quantity 8 a to the 7 over b cubed square root c. Okay, so I want to put in the multiplication symbol in the top so I don't forget. And I do have another one in the bottom, but what is important about the b and the c in the denominator is they're in the denominator. So they should go with negative logarithms. So here's what this will look like. Log base 2 of 8 plus log base 2 of a to the 7th minus log base 2 of b, cubed minus log base 2 of square root of c. Okay, so again, I want to point out I put the negative in front of the log with the c in it because the c came from the denominator, just like the b did. Okay, now I have two more things to do. I need to clean up these exponents. Can convert a square root to an exponent by making it minus log base 2 c to the 1/2, so I can treat that 1/2 as an exponent. And also, this is really easy to overlook. Log base 2 of 8 is a log that I can evaluate. What is the exponent I put on a 2 to make an 8? That exponent is 3. Okay, so whenever you can evaluate a log, make sure you do that. Log base 2 of a to the 7 becomes 7 times log base 2 of a. Log base 2 of b to the 3 becomes 3 log base 2 of b. And the 1/2 comes out also, negative 1/2 log base 2 of c. Great. Let's do a couple problems where we go the other direction and condense. So now let's condense each of the following into a single logarithm. For the first one, let's do ln of 7 plus 6 ln of y minus 8.2 ln of z. Okay, just like the last problems, the first thing that we need to get rid of is the last thing that we did on the last problems. So if we're going the other direction and we're condensing, we need to move these coefficients up and make them exponents so that then we can use rules 1 and 2 for truly condensing multiple logarithms into a single log. So that will look like this. ln of 7 plus ln of y to the 6th power minus ln of z to the 8.2. Quick note, it's up to you whether you move the negative up with the 8.2 or leave it. If you move the negative up with it, you want to make this a plus right here. That negative exponent will make it go to the denominator anyway, but it's your choice to move the negative to the exponent or not. Okay, now that we have at least positive 1 or negative 1 as all of our coefficients, now we can combine them into a single logarithm, making this ln of 7 times y to the 6th, and then divided by z to the 8.2. We're finished. Let's do a couple more. If we had, let's say, 1/2 log x minus 5.1 log y plus log z. And let's give ourselves some separation here with the last one. Okay, same directions, we want to condense, and just like in the previous problem, the first thing we want to do is take these coefficients and move them up as exponents. So this will become log of x to the 1/2 minus log of y to the 5.1 plus log of z. Okay, last step is to condense these all into a single logarithm. Since they all have base 10, that's really important. Base 10's all here. These were ln's, so they're all base e's. Then we can condense. If one of them were different, we couldn't combine them. But these are all the same base, so we can combine them. So let's see. The ones that are positive will go in the numerator. So that would be log x 1/2. So x to the 1/2 is in the numerator. And the plus log z is positive, so the z goes in the numerator also, multiplied to the x. The y to the 5.1 comes from a negative logarithm, so that will go in the denominator. Let's do one last example. Let's condense the 3 log base 7 of x minus 2 log base 7 of x minus 5 plus log base 7 of x plus 4. And just for the sake of emphasis, I'm going to add plus log base 5 of x. Okay, first thing we want to do is, just like in the previous examples, take these coefficients and move them up as exponents. So that would make this log base 7 of x to the 3rd minus log base 7 of x minus 5 squared. The last two don't have coefficients, so they're just going to stay plus log base 7 of x plus 4 and plus log base 5 of x. Okay, here's why this is important. Log base 7, log base 7, log base 7 can all be condensed into a single log. But it's not really like terms, shall we say, with the log base 5. So the log base 5 is going to have to stay separated. Okay, everything that's positive will be in the numerator of our log, and everything that's negative will be in the denominator. So in the numerator of the log, we have the positive from the x to the 3rd and the x plus 4. So we have x to the 3rd times x plus 4. In the denominator, we have x minus 5 squared. And again, that log base 5 of x doesn't have the same base as the previous with the log base 7s, so it stays there. One quick point I'd like to mention, there is no property for addition or subtraction inside a log. All of our properties deal with multiplication, division, or exponents, which is really just repeated multiplication, inside the logarithms. The addition and subtraction is outside between two separate logarithms. What we have here is addition or subtraction inside a logarithm, and there is no property for this or this to simplify the x minus 5 or the x plus 4. So we just leave it as part of the argument in the log.